Welcome to Module 2 of the Mali GPU training, Mali GPU Essentials. In this video, we will introduce the Mali GPU family, describing the evolution of the architecture and its capabilities, from the Mali 400 series to the latest GPUs such as the Mali G78, which uses our Valhall-based architecture. Mali GPUs are used in a wide variety of consumer electronics, ranging from smartphones to digital televisions to virtual reality headsets. Over 1 billion Mali GPUs were shipped in 2019. The earliest Mali GPU designs that you may still see in some devices today are the Mali 400 series, based on the UTGuard architecture. This family of small, area-efficient GPUs only support OpenGL ES 2.0, but can still be found in many older devices. The UTGuard family uses separate shader core hardware for vertex shading and fragment shading. The Pixel processor is a multi-core design, with up to 8 processors in the case of the Mali 450, allowing chip designs to scale up fragment shading performance as needed. As with many of the original OpenGL ES 2.0 GPUs, there are some functional differences across the shader stages. The geometry processor cannot support texturing and vertex shaders, and the Pixel processor cannot support high-precision 32-bit arithmetic operations and fragment shaders. The Pixel processor instruction set is a SIMD instruction set, exposing vector 4 floating point 16 instructions to each fragment, so writing vectorizable shader code is important. Most importantly, UTGuard set some of the initial design choices, some of which remain true in the current hardware today. Each Pixel processor implements tile-based rendering, shading 16 by 16 pixel tiles to completion into a local tile memory inside the shader core, then writing the completed tiles back to memory. The performance of each Pixel processor is designed to sustain 1 bilinear filtered texture sample per cycle, 1 blended fragment per cycle, and 1 emitted pixel per cycle. The shader core exploits the efficiency of the local tile memory to implement very low cost and low bandwidth 4x multi-sample anti-aliasing. This is provided by fast blending into tile memory, and the ability to resolve the frame buffer into a single sample when writing the tile back into main memory. Midgard is the second Mali architecture family, designed from the ground up to support the feature requirements of OpenGL ES 3.0 and OpenCL APIs. Midgard has 2 major sub-architectures, with the latter of the 2 also capable of supporting the Vulkan API. Midgard follows in the footsteps of UTGuard, with the same fundamental shader core throughput per clock, but is built around a new unified shader core. This shader core design can run all the shader stages, and support all the additional feature functionality required by OpenGL ES 3. Midgard also sees the introduction of many new technologies designed to reduce bandwidth and improve energy efficiency. Constant tile elimination optimizes user interfaces and 2D games by skipping frame buffer writes for tiles that are the same as the content already in memory. Forward Pixel Kill provides Mali with a cost-efficient hidden surface removal scheme, allowing occluded fragments to be discarded before fragment shading even if drawn back to front. ASTC support, Adaptive Scalable Texture Compression, introduces support for the state-of-the-art compressed texture format, allowing the compression of almost any asset with high image quality and a flexible choice of bit rates. Finally, we see the first GPUs with AFBC support, ARM Frame Buffer Compression, which enables transparent, lossless compression of frame buffers, saving yet more bandwidth for frame buffer accesses. The unified shader core used in Midgard GPUs has 3 parallel pipeline classes, known as the tri-pipe, with a variable number of arithmetic pipes depending on the specific product configuration. Like the earlier UTGuard architecture, the arithmetic units expose SIMD instructions to each thread, although the SIMD width doubles to 128-bit, and now supports 32-bit data types. The Midgard shader core is a massively multi-threaded core, supporting up to 256 concurrent threads. The supported number of threads depends on the number of registers used by the shader program. Running 256 threads requires each thread to use just 4 128-bit vector registers. More complex programs can use more registers, with both 8 and 16 register allocations possible. But this causes a proportional decrease in the concurrent thread count. Bifrost is the third Mali architecture family, designed to significantly improve performance and energy efficiency. The GPU designs based on the first iteration of the Bifrost architecture are similarly sized to the earlier cores. Each shader core can process one bilinear texture sample and write one blended fragment per cycle. Two new major architectural technologies are introduced in this first wave of Bifrost products. Index-driven vertex shading changes how vertex shading is managed, splitting vertex shaders into two and only running the position shading for referenced index values before clip and cull. The second part of the shader only runs for vertices that are part of the primitive that is not culled. Floating point frame buffers allows shaders to write into floating point render pass attachments, enabling a class of HDR rendering. Although it is worth noting that in this generation of hardware, there is not any support for AFBC compression of floating point attachments. The biggest changes in the Bifrost family are in the shader core. In this design, Mali moves away from SIMD vector instructions towards a scalar instruction set, and packing multiple threads together in SPMT, single program multiple threads warp. Warps are 4 wide, with each seeing a 32-bit data path for either scalar 32-bit operations, vector 2 16-bit operations, or vector 4 8-bit operations. On paper, the peak performance of these cores is lower than the earlier Midgard cores, 24 floating point 32 operations per clock versus 42 in Midgard. But in practice, it's so much easier to get performance out of warp hardware that the arithmetic performance measurably improves for most workloads. To help with more complex shader programs, the shader register file capacity increases, with up to 384 threads running in each core, each with 32 32-bit registers when running at full thread capacity. More complex shaders can use more than 32 registers, with a maximum of 64, but doing so will halve the thread capacity of the core. The second generation of Bifrost cores add a few incremental features, but make a radical change to the shader core sizing to improve efficiency. This generation of designs doubles the width of the shader core. Tiles are still 16 by 16 pixels, but the core designs move to 8 wide warps, and can complete 2 bilinear samples per clock, and 2 blended fragments per clock. This widening allows a rebalancing of the design that results in a new shader core that is both significantly smaller and more energy efficient than the 2 old cores it replaces, for almost identical performance per clock. In a power-constrained market like smartphones, improving energy efficiency is the only way to achieve user-visible performance increases. This generation introduces a new texture unit, which provides anisotropic texture filtering, faster sampling of YUV video surfaces, as well as more flexible AFBC support to work with Vulkan's image views. The latest Mali GPUs, at least at the time of writing this, are the Valhall family. The Valhall GPUs implement a number of changes to improve energy efficiency, with new arithmetic pipelines and a new texture filtering unit. This is the first Mali generation where the performance of texturing is higher than the performance of the fragment retire path, doubling to 4 bilinear samples per clock. This is ideal for content using more complex texture filtering modes, or making use of shaders with a high density of texture samples such as blur filters. This generation of hardware also introduces a fixed function blend path for FP16 floating point frame buffer attachments, multiple clock domains to allow shader cores to be clocked more slowly than other GPU components, and frame buffer compression for any 32-bit per pixel format including floating point formats. The Valhall GPUs implement a new arithmetic unit. Each shader core has 2 processing units, each operating on 16 wide warps, and containing 3 processing pipelines. The FMA pipeline handles the majority of floating point operations, including the fused multiply accumulate operations that are so common in graphics shaders. The CVT pipeline handles a variety of simpler arithmetic operations, including format conversion. The SFU pipeline handles processing of special functions, such as logarithmic, exponentiation, sine, and cosine. These are much less common in shader code than generic math operations, so this unit is a quarter width unit, issuing each 16 wide warp over 4 clock cycles. There are many Mali GPUs on the market, each with a different set of features and evolving performance from generation to generation. To help identify which GPUs support which features, and budget your shaders more effectively, we publish a Mali datasheet containing the features and speeds and feeds of each of our recent GPUs in a handy quick reference format. You can find this on developer.arm.com. In the next video, we will look at how the design decisions you make during game development can impact performance on mobile. We'll offer some tips and best practices to help you avoid common problems, and ensure the best performance from Mali GPUs.